Hey, hello everybody. Hey, this is going to be a video on help with question of the day on 12.2. And what we're going to do here is we're going to do the example in the book on, I believe it is page 153. Hold on a second. Yes, page 153. Which has to do with a baseball. Now, the question of the day for 12.2 is going to have to deal with a golf ball, but you're going to get some of that same information in this video. And because it is Wednesday morning, I'm going to be recording this for these guys out here, and so I'll probably be ignoring this and talking about that other stuff. Okay, so a pitcher hurls a 145 kilogram baseball past a batter at 42 or 40.2 meters per second, which is about 90 miles an hour. Find the resistive force acting on the speed at this speed. So if you guys remember Model 2, okay, and let's just talk about it in terms of if it was going straight down. So we're going to have mg, that's the force of gravity, calling that positive. And then we're going to have some sort of resistive force. And you may remember that this resistive force is equal to K1V plus K2V squared. So remember, there's always two resistive forces, one that's proportional to the velocity and another one that's proportional to velocity squared. So that's super complicated, but as it turns out, and I've said this in the other lecture, one is going to predominate. So if you think about yourself going through a fluid, like walking in a swimming pool, or even like diving or swimming under the water, you're not going to be able to go very fast, right? So you're never really kind of get into this realm. So if you're going through something that's very viscous, you're not going to end up dealing with this. And if it is, if you have a fluid that is not very viscous at all, like air, hardly viscous at all, then this essentially is going to go away, and then we're in this one. Okay, and from the other day we called this Model 1 and this Model 2. And this is in Model 2. So whenever you see something in air, it's going to be Model 2 unless I say that the resistant force is proportional to velocity. And if it's proportional to velocity, then this resistive force is equal to BV. So that can happen with things like styrofoam, which you're going to see on the problem set, or a snowflake or something like that. But otherwise, it's going to be this. All right, so now the resistive force, and I didn't go through the derivation like I did Model 1, is 1/2 d rho a v squared. 1/2 d rho a v squared. So this right here is the drag. That is the drag coefficient, okay? And that is experimentally determined. So you kind of have to do a wind tunnel thing, and various objects are going to have that. There are going to be certain regular objects that you can probably look up and get a drag coefficient, probably like spheres or cones and stuff. But for the most part, you need to determine what it is. Now, some of the information that we need for this question is in table 6.1, I think, or whatever. I'm gonna show you here in a second on the board, and you are going to need to look up that to get the cross-sectional area. Okay. Now, I could have made it harder and give you the radius of a golf ball, then you could figure out the cross-sectional area using pi r squared. But so if we go back one page and we look up here, okay? So here's a baseball, there's its radius, there's its mass, which I already gave you, and here is the cross-sectional area, That's the cross-sectional area. And right there is its terminal velocity. So we're going to need these two things, okay? And on the question of the day for the golf ball, you're going to need this cross-sectional area there, okay? So at any rate, we need the cross-sectional area of the baseball is 4.2 times 10 to the negative 3. That's square meters, and we need the terminal velocity is 43 meters per second. Okay. All right, so now we can go back to the question. And all right. So remember that the sum of the forces in the y is equal to ma. Sum of the forces is equal to ma. But once we reach terminal velocity, of 43 meters per second, those two forces are balanced. Those two forces are balanced, and therefore the acceleration is going to be equal to 0. Okay, so we would have mg minus 1/2 d rho a v terminal squared is equal to 0. And since we can take this negative and bring it to the other side, okay, then we can just say mg is equal to 1/2 d rho a v t squared. And all right, so what we first need to find is what the drag coefficient is, and we have all that information. So we just need to solve for this, so that we're going to multiply by 2 and get 2 mg, and then we're going to divide by rho a vt squared. And that will be our drag coefficient. Okay, so we're going to have 2 times 0.145 kilograms. Now, you want to pay attention. You want to pay attention to units. And in the question of the day for 12.1, okay, when I did the problem on the video, I kind of kept the standard units. And if you looked more particularly at the solution in the book, they ended up having it in centimeters, and the acceleration due to gravity would have then been 980 centimeters per second squared, as opposed to 9.8. So as long as you're paying attention to all of the units, then you're good. So the units that you're going to have to contend with on the question of the day for 12.2 is that I give you an initial velocity in miles per hour, and the terminal velocity is given in meters per second. Okay, so you just got to make that conversion. All right, so now we're going to have 9.8 meters per second squared, and our density. This is the density of the air. And although it can change due to temperature, okay, for the most part, it's about 1.2 kilograms per cubic meter, and if you think about that, that's kind of surprising, okay? That means that a cube of air, okay, kind of about like this, right? A cube of air is over 2.5 pounds. Doesn't seem like it would be that much, but it is. Okay, cross-sectional area, 4.2 times 10 to the negative 3. 4.2 times 10 to the negative 3, and that's square meters. And then we're going to have velocity squared, and our terminal velocity is 43 meters per second. 43 meters per second. And again, that gets cubed. That gets cubed. So let's go ahead and do that calculation. And if you guys would do this to make sure I don't screw up. So 2 times 0.145 times 9.8 divided by 1.2 divided by 4.2 times 10 to negative 3 divided by 43 squared. Okay, I'm ending up with 0.3049. So we'll call it 0.305. So our drag coefficient is 0.305. Now, if we want to think about the units, here, we're going to have kilograms that cancel out. We're going to have meters squared and meters cubed. Okay, so that's going to get rid of this one and get rid of that. We're going to end up having meters squared and a meter, so we're going to end up with a meter there. And then we're going to have a meter and a meter up there, so that's going to cancel out. And now we're going to have seconds squared on the bottom. And then we're going to have seconds squared, but this is the bottom of the bottom, the numerator or the denominator of the denominator, so it goes to the top. And now we're going to end up with seconds squared. So there are no units. There are no units for this drag coefficient unless I messed up. Okay, so we can kind of check that. Now, a lot of times, particularly when you get into really confusing problems and you feel like you're doing it right, but you're not getting the right answer. Okay, sometimes if you check your units and make sure everything is canceled out to the units that the answer should be in. For example, if you're looking for velocity and your units do not reduce down to meters per second or miles per hour, something like that, then you can kind of get, that's a good clue, is that you kind of messed up a variable, flipping it from the top to the bottom or vice versa, something like that. Okay, so now the next question is find the resistive force acting on it at this speed, okay, at that speed, okay, and now we can just actually just do this equation right there, and we can have 1/2 times, and let me rewrite that. Okay, so our resistive force is 1/2 d rho a v squared. So we're going to have 1/2 times 0.305 times 1.2 times 4.2 times 10 to the negative 3 times 40.2 squared, and we're gonna do the units here in a second. So I'm getting 1.24. Okay, so remember, this had no units, this had no units. This was kilograms per cubic meter. And this one was square meters. And this one was meters per second squared. So this is meters to the fourth divided by meters cubed, which would be everything but meters. And now we're going to have kilogram meters per second squared. What should our units be if we're asking for the force? What is the resistive force? What should our units be? And if you're thinking newtons, because that is a force, that is correct. Okay, but remember, force is equal to ma, which is kilograms, a meters per second squared. So this kilogram meter per second squared is in fact newtons, which is what it should be. And I'm going to come check the book because we're just doing an example, and they're getting an answer of 1.2. So I was not very careful with my units. I mean, my significant digits, but they got 1.2, we got 1.24, so I think we did the math right. Yes, sir.
I have a question about the drive coefficient.
Yeah.
Were you saying that it's supposed to end up having no units?
Yeah. Now, but sometimes it is not that that way. For example, the B in the Model 1, okay, ended up having units of something over seconds, or seconds to the -1, or hertz. So sometimes you're going to get units that actually do have units, but in this particular case, there is no units. Now, another example of that is the coefficient of friction. The coefficient of friction is a ratio of the frictional force to the normal force, and so the forces cancel out. So you're just essentially getting a ratio. So you're kind of getting, you can think of it as kind of like a percentage, right? So this would be, you're kind of getting like a 30% resistance is one way to think about it. Perhaps that doesn't quite make sense here, but that is one way to think about it. So anyways, we end up with this 1.24 newtons. All right. Now, in the question of the day for 12.2, which is going to be the golf ball one, okay, you may notice that I'm asking for that acceleration, okay, and so once you end up doing the sum of the forces is going to equal to ma, okay, you can think of now I got to think about it. So if we have a golf club that's coming down and hitting it, and it's going to go this way, you're just talking about this resistive force, right? But you want the acceleration. So instead of saying F equals ma, you're going to have this divided by m, and that will give you that initial acceleration. So what we're not talking about here is, once at least, we're kind of ignoring the fact that gravity would be pulling it down. Okay, and since I did not give you any direction, okay, you're kind of ignoring that gravity that would be acting on it as soon as it was hit. So it would be just that, and to change from that resistive force to the positive force. Sorry, the resistive force to the acceleration, you're going to divide by m. Now, can an object go greater than its terminal velocity? Can an object go faster than its terminal velocity? Okay. Why do you say yes, or why do you say no?
Yeah, because its terminal velocity is final, is like ending like resting velocity. As it's approaching that terminal velocity, it can probably at higher speeds or higher velocity.
Okay. So most people, when they think or have been introduced to terminal velocity, is, I think, oftentimes when you're talking about skydiving, if you're going to jump out of a plane, how fast are you going to go down? Now, that can vary. Because of the cross-sectional area. Okay, now the density of the air is going to be the same. So you probably have seen, if you spread out like this and try to make yourself as big as possible perpendicular to the direction you're going to increase your surface area, and therefore you're going to have more of a resistant force and you're not going to go as fast. Same thing if you are looking for that acceleration, you would divide by m, okay? So if you were to divide by a bigger number, let's see, I'm trying to think. If you're going to divide by a bigger number, your acceleration due to the resistant force is going to be less, and therefore you'd go faster. So if you had two people all with the same parameters, same drag coefficient, same cross-sectional area, but one person was heavier or more massive, they're going to fall faster. Okay. Now, if you change your shape, and you kind of put your head down and try to go straight down instead of trying to increase your surface area, if you try to decrease it, then you can end up going a lot faster. Okay. With all that being said, if you're just floating there, okay, if you're just kind of essentially not floating, but relative to the moving, you're not going any faster because what is pushing you down is gravity. What if you had a jetpack on and you were pointing straight down? Okay, you could go faster than your terminal velocity. So the terminal velocity is that measurement as if you were just essentially working against gravity, if you were just kind of falling. So if you think about a meteor coming into the contact with the atmosphere, it's going to be going a lot faster than terminal velocity, right? That it's going to end up having a huge deceleration. It's going to have a huge deceleration because it's going to be greater. So this right here, this VT squared, this can be greater, right? And then just you're going to have a greater sort of acceleration in that negative direction. All right, I think that covers it as far as help with question of the day 12.2.